Hello students, today we will discuss some theorems on sequences. First theorem, a sequence Sn in R has at most one limit, that is limit of a sequence is unique. So you take any sequence, when you are applying the limit, then it should have one limit value. So for that, to prove this, we are assuming that suppose it is having more than one limit values, what will happen? Let us see. So to prove that limit of a sequence is unique, we are assuming that Sn has more than one limit value. Suppose I am taking two limit values, L1 and L2 are the limits of Sn. Suppose we are taking first L1 is the limit of Sn, then by definition of limit, what is the definition of limit? For all epsilon greater than 0, there is a natural number such that modulus of Sn minus L1 less than epsilon actually. So this is the definition for limit for n greater than or equals to m. Here we are taking two limits, means here we are taking L1 and here instead of m we are taking m1 here. Similarly, L2 is the limit of Sn. So what is the definition for limit of Sn? Sn minus L2 less than epsilon. So here also for all epsilon greater than 0, there exists m2 belongs to natural number such that modulus of Sn minus L2 less than epsilon for n greater than or equals to m2. Why we are taking epsilon by 2? We will discuss later. Now, consider L1 minus L2. What we need to prove? It should have only one limit value. Suppose we are taking two limit value, they must be coincide, that we need to prove. For that, considering L1 minus L2 and adding and subtracting S1 for this, and take these two at a time, Sn minus L2 here, minus take common here, then minus common means Sn, minus take common means minus L1. So we are taking modulus of A minus B. By triangle inequality, modulus of A plus B less than or equals to mod A plus mod B. Similarly, A minus B is also can be written as what? Modulus of A plus of minus B. So here modulus of A plus B is less than or equals to mod A plus mod B, means mod A plus mod minus B, it is nothing but B. So modulus of A minus B is also less than or equals to mod A plus mod B according to triangle inequality. Now see here, mod A minus B can be written as less than or equals to mod of first part plus mod of second part. So mod A plus mod B. So here mod Ln minus L2 is less than epsilon actually. This is also less than epsilon, but we want less than epsilon here. That's why we are, for our convenience, we are taking epsilon by 2 here, epsilon by 2, because when you are taking epsilon is very, very small quantity. When you are taking by 2, then it will be very, very small, right? We are taking a small part into two parts, then the one part is so much less part, right? Like epsilon by 100, we are taking into 100 parts, one piece is a very small quantity. So epsilon is a small value, that's why we can take as instead of epsilon by 2, epsilon by 3, then it will become a very, very small value. So according to our convenience, we can take as epsilon by 2 here. That's why we are taking here epsilon by 2, epsilon by 2. So here this is nothing but epsilon. So mod L1 minus L2 is less than epsilon, means it is a small quantity. So it is very, very small quantity, means almost tends to 0. So we can say L1 minus L2 equal to 0, means L1 equal to L2. That means when you are taking two limit values, more than one limit values, then also it is coincide. That is L1 is equal to L2, means limit has a unique, a sequence has a unique limit value. So here prove that another theorem, the limit of sum of two convergent sequences is the sum of their limits. That means you take any two sequences, take the sum and apply the limits, then we can split the limit, like limit of Sn plus limit of Tn, which is, suppose it is considering limit of Sn is k, some limit of Tn is L, then limit of Sn plus TL is nothing but k plus L, which is nothing but limit of Sn plus limit of Tn. This we need to prove. For that, take one sequence Sn, which is a convergent sequence, means whose limit value is k. So according to definition, what we can write? For all epsilon greater than 0, there exists m belongs to n such that modulus of Sn minus k is less than epsilon. For our convenience, we are taking here epsilon by 2 for all n greater than or equals to m. Similarly, Tn is a sequence whose limit value is L. That's why according to the definition, Tn minus L less than epsilon by 2 for n greater than or equals to m. Now to prove this one, to prove limit of Sn plus TL equal to k plus L. So according to definition, what we need to prove is, for all epsilon greater than 0, there exists m belongs to n such that modulus of sequence is this one minus limit value is k plus L less than epsilon. modulus of Sn minus Tn minus limit value is k plus L, which is less than epsilon for n greater than or equals to L. So, to prove limit of Sn plus Tn equal to k plus L, by definition we need to prove like this. Modulus of Sn plus Tn minus k plus L less than epsilon. For that, consider the left part. Take this. And Sn minus k, take it a time, and Tn minus L. Sn minus k plus Tn minus L. Now again, modulus of a plus b is less than or equals to mod a plus mod b according to triangle inequality. So this is nothing but epsilon by 2 by definition of limit of Sn equal to k, and limit of Tn equal to L in the sense this is less than epsilon. So for our convenience we are taking as epsilon by 2 which is less than epsilon. So this total is less than epsilon means according to the definition of limit, how you can represent in notation, limit of sequence Sn plus Tn equal to k plus L. But what is k here? According to the question, limit of Sn equal to k, that's why k equal to limit of Sn plus limit of Tn. So hence proved. Similarly, we can take the difference also, limit of Sn minus Tn equal to limit of Sn minus limit of Tn. That is, limit of difference of two sequences converges to the difference of their limits. That means for subtraction also we can split the limit. Same, instead of addition we can take the subtraction symbol here. Sn is a convergent sequence. So by definition of Sn, modulus of Sn minus k less than epsilon by 2. Similarly, Tn limit value is L, that's why by definition of this, Tn minus L less than epsilon by 2. Now consider to prove what? Limit of Sn minus Tn is nothing but k minus L, which is nothing but limit of Sn minus limit of Tn. By definition, what we need to prove? Modulus of Sn minus Tn minus k minus L less than epsilon. So this we need to prove. For that, consider this part, and Sn minus Tn minus k minus into minus plus L. Now take Sn k at a time, that is Sn minus k. Take minus common here, then Tn minus L here. So modulus of a minus b less than or equals to mod a plus mod b. Already we have discussed previously. So this is nothing but less than epsilon by 2, which is nothing but less than epsilon by 2. So it is less than epsilon. So according to the notation, this definition converting into a notation as limit of sequence equal to limit value, that is limit of Sn minus Tn equal to k minus L, where k equal to limit of Sn minus L equal to limit of Tn. Similarly, we can prove another theorem. Limit of Sn equal to some k, finite value is given, p is any real number that is given, then prove that limit of p into Sn can be written as p into k, which is nothing but p into limit of Sn. That means constant into any sequence. When you are applying the limit, take the constant outside, then apply the limit for the sequence. This we need to prove. For that, obviously Sn is a convergent sequence, so limit value is L. That means by definition we can write as modulus of Sn minus k less than epsilon. For our convenience we are taking by p. Later we will discuss this one. So p is any real number means to prove this part, so p into limit of Sn. For that, by definition what we need to prove? Modulus of Psn minus limit value is pk here less than epsilon. To prove this, consider this part. Now take p as common from these two, and modulus of a into modulus of b means modulus of a mod a mod b, of course, but mod p is nothing but p, and p into Sn minus k here. But here mod Sn minus k is less than epsilon actually, but here into p is there, that's why we are taking divided by p here, because epsilon, when you are dividing into small parts, there is no difference in between epsilon and epsilon by p. So instead of epsilon we are keeping here epsilon by p, then p gets cancelled. Now we are getting epsilon. So this is less than epsilon in the sense limit of Psn equal to pk. P into what is k here? Limit of Sn. That's why we can take p into sequence limit value is nothing but p, take it outside and apply the limit for the sequence. Now we will see one more theorem, and limit of Sn equal to k and limit of Tn is L, which is given, and limit of Sn into Tn we can prove as k into L, that is nothing but limit of Sn into limit of Tn. That means when you are taking the product of any two sequences limit, then we can split the limit for that product also, limit of Sn into limit of Tn. To prove this, obviously we are writing the definitions. Limit of Sn equal to k means modulus of Sn minus k is less than epsilon. By what we are writing, let us discuss later. and limit of Tn is equal to L means according to the definition Tn minus L less than epsilon. For our convenience we are taking here 2 by m. Let us see later. Now to prove limit of Sn into Tn equal to k into L, which is equal to limit of Sn into limit of Tn. To prove this, by definition what we need to prove? Modulus of Sn into Tn minus KL is less than epsilon. For that consider obviously left side value. Up to here, okay. Now what we need to do is, there is no common here. That's why what we are doing is adding and subtracting some sequence and other limit value, that is Sn whose limit value is k, Tn whose limit value is L. That's why Sn into other limit value is L. So Sn into L, we can add and subtract Sn into L for this term. Or else you can add Tn into limit value of Sn is k. We can also add and subtract Tn into k. Otherwise we can add and subtract Sn into L. For our to prove product of two sequence is equal to product of their limits means we need to add and subtract this term, and from these two we can take Sn as common, then Tn minus L. From these two take L as common, then Sn minus k. Similar again, modulus of a plus b less than or equals to mod a plus mod b according to triangle inequality. And also here mod a into b in the sense mod a into mod b. So mod Sn into mod Tn. Here also mod L into this one. Up to here okay. But what we know is every convergent sequence is bounded. Here we have one theorem that every convergent sequence is bounded. So this proof we will discuss in the next video. So see here, every convergent sequence means a sequence which is having the finite limit value, then it must be bounded. And the bounded condition for any sequence is modulus of Sn less than or equals to m. This is the condition for bounded sequence. We will discuss in the next video this one. Okay. Now this is a convergent sequence, of course, whose limit it is also. So every convergent sequence is what? Bounded. So according to bounded definition, modulus of Sn less than or equals to what? Capital M we can write. So here instead of Sn we can write less than or equals to m. Take this part as it is. Again this is also Sn limit value. That's why it is also bounded. So it is also less than or equals to m. Less than or equals to m. And take the remaining terms as it is. Now Tn minus L. Tn minus L is less than actually what? Epsilon. For our convenience here we are taking suppose divided by m means divided by m. Then m gets cancelled of course. Again epsilon is getting. So epsilon plus epsilon, 2 epsilon will come. That's why we are taking divided by 2m. Then what will happen? M gets cancelled here. Here this into Sn minus k is also less than epsilon by any number we can write. Here I am writing here 2m, then m gets cancelled, then epsilon by 2 plus epsilon by 2, it will become epsilon. That's why for our convenience we are taking here by 2m. Now what is happening here? Modulus of Sn minus Tn Tn minus KL is less than epsilon. So according to the limit notation, what we can write? Limit of Sn into Tn equal to k into L. So k is nothing but limit of Sn, L is nothing but limit of Tn. Hence prove. Here some more problems on limits, evaluation of limits. Suppose one sequence is given, find the limit value of the given sequence, then find limit of this part. So here root is given. When you are taking as n tends to infinity, infinity will come. That's why we can take the rationalization of this one. So if root is given, take rationalizing means take the same term with opposite sign. That means here root n square plus 1 minus 1 n is given. So root n square plus 1 plus n divided by same term. Then it will be rationalized. Now a minus b into a plus b means a square minus b square. Root n square plus 1 whole square means root n square gets cancelled, n square plus 1 minus n into n square divided by denominator as it is. Now gets cancelled. Now as n tends to infinity, 1 by this term. So as n tends to infinity, what we are doing actually? Take highest power is common in numerator and denominator. Of course in the numerator there is no n term. In the denominator we can take n square common here. Then 1 plus 1 by n square here plus n as it is. Now n square take it outside, then it will be what? N. So n into root of 1 plus n square plus n here. Now take n common from these two. Now n common means same term plus 1 here. As n tends to infinity, 1 by n tends to 0. 1 by infinity is 0. So 1 by n tends to 0 and 1 by n square is also tends to 0. Now substitute all those values, then 1 by n is nothing but 0. 1 by root of 1 plus 1 by n square tends to 0 plus 1. So a 0 into anything is 0. That's why the limit of the given sequence is 0. Another problem, limit of same root value is given means we can take rationalizing by taking with opposite sign in the numerator and denominator. Now a minus b into a plus b means a square minus b square. A square means this square means root and square gets cancelled, minus 2n whole square means 4n square divided by same term. Again gets cancelled, n divided by, here from the root n square taken as common means 4 by n square is 1 by n plus 2n as it is. N square take it outside, then n it will be n taken as common from first and second term, then n of root of this plus here n common means here 2. Now n gets cancelled. Now it will become like this. As n tends to infinity, 1 by n tends to 0. That's why we can substitute n 1 by n as 0. Then 1 by root of 4 plus 0 here plus 2. 1 by root 4 is 2 plus 2, that is 1 by 4. Similarly, we can see the next problem. Same rationalizing. So here plus numerator and denominator same term multiplied with the same term, and here a minus b into a plus b is a square minus b square gets cancelled, denominator as it is. Now n, take n square is common from this root, then 1 plus 1 by n here plus n as it is. Now take n square outside, then n it will be n into this. Again take n is common from these two, then n common means root of 1 plus 1 by n plus n common means here 1. N gets cancelled here, as n tends to infinity, 1 by n tends to 0. Now substitute 0 here, then it will be 1 plus 2. So in the next video, we will continue some more theorems on sequences.